very happy to introduce Maxim Totrov from representing MolSoft. He's going to give the first participant talk for GC3. So welcome, Maxim.
Thank you, Rami. So Max Totrov is from MolSoft. If you have heard of us, we are a small company here in San Diego. We develop ICM, which is this package of various molecular modeling tools. But docking was always a central part of it, especially ligand docking. And so we were really excited when we learned about grand challenges organized by Rami and Mike. Well, we didn't know about the Grand Challenge 1, but Grand Challenge 2 and on, we participated, tried our methods in post predictions and now also in affinity predictions as well. Let me start with just the introduction, some overview of our methods. So how do we dock molecules, since both post prediction and affinity predictions based on that. Just some key points of our algorithm are that we start with pre-sampling the ligands, so generate lots of conformations, then we put them into the active site in a bunch of orientations, start some short Monte Carlo trajectories from there in torsion space, minimize them, gradient minimize and sample, and then generate a bunch of poses this way. The receptor, as you imagine, with the grid potentials is static, but we can have either part of the receptor explicitly there, or we can sample conformations by ensemble approach to generate a bunch of maps or grids and switch between them as we proceed in the Monte Carlo simulations. Then the poses generated through this procedure are re-ranked with a little bit more rigorous score that includes explicit receptor. I will discuss the score a little bit more later on. But this is basically the core protocol. It docks a lot of ligands pretty successfully. There have been different benchmarks where we do competitively, but the point is at some point when you face a shallow pocket or you face a receptor that has a lot of flexibility, like many other methods, you get problems, you get artifactual poses, etc. And as many others, we would try to impose some sort of constraints or other ways of directing the simulations towards something that resembles known experimental poses. I will focus on one approach that we in particular worked on recently, which is biasing by what we call APF, using the experimental or otherwise templates ligands. What are these atomic property fields? Some while ago, I published this paper. So the idea here is to represent the ligand as a bunch of fields that encode the different phys-chem properties. And these are sort of more traditional, in some case, pharmacophoric properties, like donors, acceptors, lipophiles. And then we try to add also some less traditionally seen properties there, such as, for instance, hybridization that sort of encodes for flatness of the structure, or, for example, electronegativity or positivity, which reflects the electronic structure. That's important too for activity, right? So these fields are, if you will, a generalization of pharmacophores going from points that have very simple basic properties of a few kinds to continuous fields that have very precise description of properties of atoms as vectors of properties, some properties I just mentioned. The field could be generated in different ways, but the basic way is to just make Gaussian fields. This has been used by other groups too. I think we have a more detailed description. That's one of the advantages there. So you could have these Gaussians centered in each atom, and proportionally to the presence or absence of a property, they would be taller or smaller. And then if you place another compound into these fields, then you could calculate a sort of pseudo energy or score that reflects basically the match of the molecule in terms of various phys-chem properties to the template. Because it's implemented as a 3D grid with gradients, we can actually include it into molecular mechanics simulations so that we can optimize this score eventually together with also force field energies. And initially this was positioned as basically ligand superposition tool, and indeed it worked pretty well. If, for instance, an assessment from an independent group like a few years ago, compared to a few, really well-respected codes. We did quite well. The only group that did, over 50% sort of correct superpositions here. Now, recently our thinking was that if this is working pretty well as a superposition tool, why not use it in combination with the docking protocol to drive the structures towards something that resembles known examples in X-ray structures. And this is exactly what we used actually in Grand Challenge 2 and 3. So we added on 2 stages this APF fields to our simulation. So firstly, during the sampling itself, we would add these potentials that are generated from the templates. They look sort of like that, there's some blobs of felicity or acceptors and donors, etc. And on the other hand, on the pose ranking stage, we can also combine our more physics-based score with this APF sort of pseudo-analysis that reflects the degree to which the pose resembles the crystallographically observed ones. So that's what we used for pose generation, in particular for Katepsian, pretty much straightforward, this algorithm. That's what we got, the red bar. So, that looks pretty good, right? In most sort of categories. Now, on average RMSD, we didn't do as well as the best pose 5, and the medians, well, they're also better. So the better half of the prediction is good, but some of the more difficult ones only are good when you look at top 5, but not maybe at just one top pose. Now, why is that? Why are we here in the middle of the pack instead of being here? Looking at RMSDs of all our poses, we find that across all ligands, yes, we find that these are the most accurate poses of 5, the red blocks. So they're all sort of reasonable, at least, sometimes under 2 and 1 even, but even the worst ones are maybe at 3. But there are 3 ligands where these pink bars are really tall, 8, 9, and 10 angstroms. These are ligands 7, 9, and 14. What happened there? Why do we get the wrong pose as a wrong? Let's see if it's wrong, but as a top pose. I looked and just want to offer a few observations there, and I'm glad that this was already brought in part by previous speakers in their talks. So one thing is, let's look at the crystallographic neighbors. So it happens to be that for these 3 ligands, if we reconstruct the crystallographic neighbor in the structure, all of them have a pretty extensive contact with a neighboring molecule, and the neighboring molecules superimpose perfectly. So basically, it's the same crystal organization. The contact is about 150 angstroms, which is like a quarter of the total contact. So there is clearly a pretty strong interaction here with the neighboring subunit. Also, on the other hand, another observation, if we look at some other ligands that also closely resemble these, they actually do show the mentioned flip of the this moiety, which I won't name not again, unfortunately, but it's flipping the other way, and we see that here. This is actually an accurate solution for ligand 16. We get that other pose, and our top 1 poses for that other 3 examples are similar to that. So it may or may not be the basically the 2 solutions are pretty close in energy, and perhaps what drives a specific conformation that is seen in the structures is, at least in part, defined by how the crystal packing is. I have to note that here actually the neighbor is in a different position, so the crystal cell is different in this structure and this. Anyway, continuing to other challenges. So for kinases, we didn't have an explicit pose challenge, but nevertheless our methods for affinity prediction are based on poses, so we wanted to get as good as possible the poses for those ligands as well. And then I'll mention in the same context FXR because in both cases, we wanted to treat pretty extensively the flexibility, unlike with the cathepsin S, where we saw that similar ligands in X-ray structures don't seem to require any extensive movements of the receptor. So the way we treated the flexibility is by using ensembles. Fortunately for all of this, there are lots of PDB structures, so we would take all of them from Pocket.on database by Ruben, and mention it a little bit more later. And then make this sort of compatibility matrix to extract a subset of structures that would be compatible with most ligands, X-ray ligands. So basically, it's a kind of interaction energies of the aligned receptors and ligands, and we take the most compatible one and add more structures to get a good ensemble that could cover at least all the X-ray ligands well. Just to mention that, of course, this can be done manually. You can collect by hand from PDB all the relevant structure for a given target, but Ruben Avagan at UCSD came up with this Pocket.on database, which was really handy and saved us a lot of time to actually, instead of taking them manually from the PDB, we just took the ensemble directly from the database. It already has all the structures aligned, variations in, let's say, numbering of residues are taken care of, and the optimal alignment of the structures is done for us. Now, this is I'm briefly mentioning the GC2 pose prediction to illustrate that this approach does work well as far as pose prediction, including these ensembles use, because I cannot show anything for poses using the same protocol on kinases. Now, let's move on to affinity prediction. So we do affinity prediction by sort of two key approaches here. In both ways, we start with docking, so generate poses, as already described. Now we have sort of more physics-based approach, which is the ICM score. It's, if you will, a combination of what is basically MMGBSA type of score, so the force field, generalized Bohr electrostatics, hydrophobic term that is, well, surface-based. And then we add a couple more terms that are sort of specific to our score. So this is a directional hydrogen bonding. We feel that electrostatic is not treating it well enough. And then complementary term, which is polar desolation for unsatisfied donor and acceptor sites. And then we have also the very simple torsion-based estimate of entropy. So this is physics-based approach. Now the alternative is more, knowledge-based, ligand-based IPF approach. So going back to those fields that I described in the beginning, imagine we could construct a field that would, instead of giving just this sort of similarity to the template, a prediction of delta G. Turns out that we could formulate such a field in terms of a linear combination of fields from template ligands. So the training ligands in this case, when we train the potential on a set of training compounds with known activities. So we get some number of weights there, and then with some simple linear algebra, we can arrive at a set of linear equations with weights, and this EAPS, the cross sort of correlations of the pairs of training set ligands. And PLS can be used to determine the weights in this equation that are optimal to produce a good prediction function. So this is the ligand-based approach. We tried it in the past on other targets. It works sort of well, and we're confident to use it as cathepsin. We trained the model on 300 related compounds from Campbell, used the poses to generate these potentials and did the predictions. That's how we did for cathepsin. Now, before I proceed to kinases, I want to discuss a little bit the availability of training sets for activity data. The reason that we could use all the 16 of training is because Campbell has really plenty of data for each of these targets. Cathepsin has over 1,000, and some of the kinases have way more still. Now, despite this seemingly similar numbers, the relevance of these sets hugely different between the sub-challenges, let's say. For Kitepsin, we really had a lot of related data. Here, the plots of minimal distance to basically closest training set ligand from each of the challenge ligands. So each and every challenge ligand here was like within 0.25, let's say, tanimoto distance, and on average is something like 0.1. So really, these are close congeners of known measured ligands. Now, when we move to VEGFR, we would see already somewhat different picture. We have still this area of congeners somewhere here, but that's less than half of them, and a significant part are in this range of 3, 4, 0.3, 0.4. These are really more difficult to predict. They're not anymore just small variations on the same scaffold. And then if we go to JAK and P38, basically the entire challenge set is mostly this more distant representative. So we wanted to try to devise a protocol that would do a little bit better than the plain APF3D QSR that I just described, because for Kitepsin it was fine, but at these distances we felt from the prior experience we might be not doing that well. We wanted to test a bunch of different protocols internally and submit one set, not a bunch of different attempts. So internally, we devised or tried to devise a training test set combination that would sort of better reflect the situation when we do a true challenge. I think too many times in the field, we evaluate our methods, we leave one out, or even, let's say, and fold cross-validation, which really doesn't reflect what happens in the real world, because you always end up with vast majority of test compounds very close to the training. So we devised instead this threefold cluster cross-validation set. So we take clusters of compounds from the complete training set and break them down into 3 groups by clusters, and then 2 are training, one is a test set. You will see how well it did as far as predicting the actual world, real world performance, let's say. Now, what did we try as far as improving on the APF and QSR, as I described already? First is the combination of APF and physics. So we know that APF produces very nice models when it's close to the training set compounds. But on the other hand, I'm a physicist by training, and I believe that eventually physics should predict farther away. It's physical laws are more extrapolatable than those trends in QSR. So can we combine this for better performance? And we try to investigate a few models that do combine them. On the other hand, what we also played with was trying to make focus models, which we saw previously may help. Basically, when you do a large QSR set training, the local trends seem to kind of just get diluted in this big volume of information from different families of compounds. So we also looked at these focused models. And this is how the focus models are made. We cluster the challenge compounds, and for each subcluster, we find sort of relevant molecules in the training set and try to train this sort of dynamic model for each cluster separately. This is the cross-validation on the cross-validation that I just described for a bunch of approaches that we took. So in the middle is this sort of baseline APF QSR TLS model. That's fairly reasonable. These are Q squares, mind you, so Q's corresponding are like 0.5, let's say. Now, physics alone, unfortunately, doesn't do very well. Trained physics with PLS could do somewhat better, but still doesn't quite get most of the time to where the APF QSR is. RFR really doesn't help versus PLS. RFR is random forest regression. It's a more sophisticated sort of modeling method, right? Or machine learning method, I should say. Now, what happens when you add physics and APF? And it happens that it looks like we actually do get some advantage from it. And in a simple model where we just combine the physical terms with those APF correlations, we get generally higher numbers apart from one target. Two-stage, we played with two-stage things, doesn't do as well. Here we actually do PLS first on APF and then add the physics terms through RFR. And this seems to be the most consistently better approach over APF only. So in each case we get, not huge but substantial improvement, and we also drive down the RMSEs, right? So that we liked, and then we also played with these focused approaches that seem to help as well if you compare the parallel numbers here and here, here and here, here and here, and here and here, there is improvement here. So we felt that this was consistently the best method, and went ahead with submission with this protocol. Now, okay. Just 2 slides. Okay. So this is the performance on the challenge set when we got the answers back, and unfortunately we are switching here from Q squares to R, so mind you, the other numbers are square roots, let's say, of these numbers. So this is the submitted model, and we do see that the cross-validation as we did it generally is quite predictive of what would happen in the challenge. So here is very close, here slightly worse in the challenge. Here is actually significantly better in the challenge than in the cross-validation. Why is that? Well, because as you remember those distributions, maybe here we have quite a bit more closer compounds, so about a third of the set is in this narrow range of distances, so that's probably why we beat the cross-validation on the challenge set. We also sort of confirmed here pretty consistently that combination of physics and APF did better. And most of the conclusions from the previous table held. However, unfortunately, this idea of static versus focus seems to have fallen flat. So we see actually similar numbers between the two. So the simpler model seems to behave at least as good, and in fact here it did better. If we submitted these results, at least in one case we would have gotten significantly better correlations. Well, nevertheless, it was our second best model, but it was pretty good in the ranking overall. So conclusions, well, since you saw the talk, so I guess you could make your conclusions. I just want to acknowledge Paul Ulam, who did most of this work, all the docking and model building. Eugene Rausch helped a lot with chemoinformatics. Ruben Avagian, well, his vision created the ICM as it is, and all the tools there are really useful for these predictions. I want to thank the D3R organizers. Of course, it was a fantastic chance for us to test our software. It inspired us to develop new approaches, and also we got an opportunity to present it now. Thank you.
We are already at least a full 20 minutes, which was a great talk. Thank you. So maybe, Gway, if you want to come on up. You're the next speaker while we get you ready. Is there maybe we have time for one burning question, but we are already past. Yes, one. David?
From combining the physics-based and the approaches, do you have any insights on what's missing from other physics course fields? Could be.
Well, unfortunately, yeah, we have to look at this closer with the fully PLS model. The PLS RFR, which we sort of focused on, RFRs are pretty opaque, so it's kind of hard to tell what they, pick there. But we now have also this plain PLS, which seem to perform comparably. And I hope for the paper we can draw more conclusions of what it takes from physics and what it takes from chemistry.
I'll give you a sign halfway through. And then